Hopefully you're looking at this and you're thinking that it looks very familiar. This is the lab experiment that we actually conducted in class. We took some iron nails and we placed them into a solution of copper 2 chloride. And so we had a single replacement reaction that was occurring where iron was reacting with copper chloride. And if you remember, we went ahead and we collected the copper in our beakers. And so if we look at the data table down here, we can see the same exact kind of data that we collected in class. We've got an empty beaker, so that way we can subtract that mass of the empty beaker from when we have the dried copper at the end, so that way when we look at the difference between these two, we can figure out, well, how much copper did we have as a product in our beaker here. We also needed to record how much copper chloride we used. We also recorded the beginning mass of our nails as well as the ending mass of our nails. So make yourself a note on your paper that finding the difference between these two is going to tell you how much iron was used in the chemical reaction. So that's going to tell you right here how many grams of iron did we use. Okay, how much of that reactant material going in. Then we also need to look and see that right here we have our grams of our copper chloride. How much of that reactant did we need? And then we also want to notice that we can find our grams of our product. So we're going to need our empty beaker and we're going to need our mass with our copper at the end. And we're going to use those two, and that's going to find our grams of our product of copper that we made. Okay, so there's a lot of information that we need to kind of process when we look at a chemical reaction like this. We want to make sure that we're understanding that we have to have an amount of materials going in, and we can figure out how many grams of copper chloride went in. We can figure out how many grams of iron went in, and then we can also figure out how many grams of copper were actually made. So again, think about this as kind of like a recipe. Remember that we have to have materials go in order to have products coming out. So the first question here says, how many moles of copper chloride did you use in the experiment? So I can see that I started with 7.2 grams of copper chloride, but I need to find out how many moles that would be. Well, I know that 1 mole of copper chloride has a molar mass, so I'm going to calculate the molar mass. So take a minute, pause the video, and calculate the correct molar mass that we're going to use in this conversion factor. So don't forget when you do that you're going to have 2 chlorines and 1 copper in that formula. So our molar mass is 134.452 grams in 1 mole of copper chloride. So since I don't want grams anymore, I'm going to go ahead, since I'm starting with grams, I'm going to put that molar mass on the bottom of 134.452. So what we actually have going on here is we're going to take 7.2 times 1 and then divide it by 134.452. That's going to tell us the number of moles. Now this is a problem from last unit. This isn't any more complex than anything that we worked on with last unit. So take a minute, again, pause the video, practice with making sure that you can put this in your calculator correctly, and calculate how many moles of copper chloride you used in the experiment. So you should have gotten 0.054 moles of copper chloride were used. Now we're going to do the same thing to calculate how many moles of iron were used, but remember that we do need to do some subtraction to find out how many grams so that then we can convert to moles. So again, take a minute, pause the video and try to do this on your own. This is nothing more complicated than what we did last unit. This is still last unit information and material. First, calculate how many grams of iron were used and then convert that to moles. So again, our first step is going to be subtracting to find out how much iron was actually used. So you should get 4.6 grams of iron. And again, this setup is going to be the same as the previous problem where we don't want grams anymore, so we're going to put grams on the bottom. We want to find out how many moles this is, so we're going to put 1 mole on the top. We're going to look at our periodic table to find the molar mass of iron, which is 55.933 grams. Again, what this does for us is grams cancels out, and we're now going to know how many moles of iron it is that we used in our reaction. So again, in your calculator, you're going to do 4.6, and you're going to divide that by 55.933, and you should get 0.082 moles of iron. Now, on letter C is when we really get into stoichiometry. It says based on 7.2 grams of copper chloride that were used in the experiment, how many grams of copper should you have made? So this problem is actually asking us something a little more complicated. I am starting with 7.2 grams of copper chloride, and we actually want to know how many grams of copper should we have made. So there's a few different relationships we're going to need to use here. The first relationship that we're going to need to use is we're going to need to go from our grams of copper chloride to our moles of copper chloride. And the reason that we're going to have to do that is because in a balanced chemical reaction, if we look up here, in a balanced chemical reaction, the only relationship that is given to us is a mole-to-mole relationship. This balanced chemical reaction right here actually says that I need 1 mole of iron to react with 1 mole of copper chloride. That's going to make 1 mole of iron chloride and 1 mole of copper here. Okay, so we're going to need, instead of grams of copper chloride, we're actually going to need our moles of copper chloride, which we actually calculated in letter A. So we've got part of this problem done for us. We actually already know that we have 0.054 moles of copper chloride. So that's the first step. Now that we know our moles of copper chloride, we can now go from our moles of copper chloride and figure out, well, how many moles of copper should we have made? So again, that balanced chemical reaction, let me bring it back down here for you and write it. So this balanced chemical reaction, if we know how many moles of copper chloride we used, we need a relationship from our balanced chemical reaction that relates copper chloride to copper. So if we look here, there's no coefficient in front of copper chloride. So what that really means for us is that 1 mole of copper chloride is needed, and we're going to make 1 mole of copper. For every 1 mole of copper chloride we make, we're going to make 1 mole of copper. So it's like a 1-to-1 ratio here. So if we have 0.054 moles of copper chloride that are going in, well, that's how many moles of copper that we should have actually coming out. And I can do that mathematically. Again, if I have 0.054 moles of copper chloride that are going in, now I can use that relationship from the balanced equation that 1 mole of copper chloride is going to make 1 mole of copper. So what that does is I cancel out my moles of copper chloride, and so I have 0.054 moles of copper is what I should have made. But we want to know how many grams of copper should we have made. So again, I started with 7.2 grams of copper chloride. I figured out how many moles that was. I looked at my balanced equation. I said for 1 mole of copper chloride, I'm going to make 1 mole of copper. So that means that if I've got 0.054 moles of copper chloride, that's how many moles of copper I'm going to make. And I know that there is a relationship that 1 mole of copper is equal to the molar mass on the periodic table, which is 63.55 grams. So now that I know that I'm going to make this many moles of copper, I can actually convert that to grams. So all I have to do is, I know 1 mole of copper has a mass of 63.55 grams. So how many grams of copper should I have made? I'm going to take my 0.054 and I'm going to multiply it by 63.55, and I should have made 3.43 grams of copper. So again, what did we do here? We really started with a material going in. This is like your ingredient. This is what had to go in. And I used it to figure out, well, how much copper should I have coming out? So first I took my grams of my ingredient, converted it to my moles. Then I used the relationship from the balanced chemical equation. Well, how many moles of copper chloride do I need? And how many moles of copper do I make? And so then I took, okay, that means that's how many moles of copper I am going to be able to make. Well, how many grams would that be? So now let's look at the data table and see, well, we were supposed to make 0.343 grams of copper. And how much copper did we really make? So I'm going to go ahead, I'm going to take, wrong spot. I'm going to take 88.44. I'm going to subtract the mass of my empty beaker, and according to my my lab experiment, I actually made about 3.18 grams of copper, which, that's not too bad, really. If I look at how many grams of copper I should have made versus how many grams I made, that's not too bad. So what we can do now is we can calculate our percentage yield. It's kind of like saying we can calculate how good of a job did we do on this lab. Did we actually make the amount of copper that we were supposed to make? So there's an equation for us to do that. So to calculate the percentage yield, we actually are going to we're going to take the actual amount in the laboratory that you got. So the actual amount is how much you actually made. So that would be letter D here, the actual amount that we made in the laboratory. And what we do to calculate percentage yield is we divide it by the theoretical amount, or the amount that we should have gotten based on calculations. So theoretically, how many grams should we have gotten? We calculated as 0.054 moles, which we calculated would be 3.43 grams. So 3.183, that is going to be our actual amount right here. And then the amount that is theoretical is going to be the amount we calculated that we should have got. And then what we do, because we do want it to be in a percentage, we do take it and we do multiply it by 100 in order to get that into a percentage. So here's what this looks like. To find our percent yield, we are going to take our actual, which is 3.18 grams of copper. We're going to divide it by the amount that we calculated we technically should have gotten in the laboratory from using 7.2 grams of copper chloride. So that's the theoretical amount. Then we're going to take that and we will multiply it by 100 so that we get it in a percentage. So we should get a 92.7% yield. So that means that we were pretty close to what we were supposed to get. So think about this. We were supposed to get 3.43 grams, and the amount that we actually got was 3.18 grams. Those two numbers are pretty close to each other. We're almost at 100% there. All right, so we have another lab example here. It says, in the lab, you're gonna do a basic reaction of baking soda with vinegar. And when this happens, when the sodium hydrogen carbonate reacts with acetic acid, it produces water, carbon dioxide, and sodium acetate. So we can actually see the balanced chemical reaction over here. Here's baking soda's formula plus vinegar. And so that's going to make water, carbon dioxide, and sodium acetate. We can check and make sure that we are balanced, because anytime we do anything here, we do have to have a balanced chemical reaction. So we are balanced here, which is good. And in order to solve any of these problems, we are going to need the molar masses of our materials. So we're going to need to know the molar mass of baking soda. We're also going to need to know the molar mass of our product, sodium acetate, because these are the things that we're going to be working with. It says you recorded your amount of sodium hydrogen carbonate. So you recorded your baking soda, and you want to figure out how much sodium acetate you should make. So that's why we're going to need the molar masses of these two. We're going to need the molar mass of baking soda and the molar mass of sodium acetate. So go ahead, pause the video, take a minute to calculate the molar mass of baking soda, the molar mass of sodium acetate, record your molar masses down here, and then resume the video to check and make sure that you calculated those correctly. So check your molar masses, 84.011 grams per mole for baking soda and 98.04 grams per mole in sodium acetate. So we will be using those. So if we look at the data table, you can kind of see how we've got an amount of baking soda that was used during the reaction. We have a weight of our empty flask, and we have the weight of the flask with the reaction with the sodium acetate. So the first question says, according to the data, you used 15.5 grams of baking soda. Calculate how many grams of sodium acetate you should have collected. This is going to be your theoretical yield. So let's just lay out first for a minute what we're doing. So what we have here is 15.5 grams of baking soda. So we know our grams of baking soda. And we want to find how many grams of our sodium acetate we should have made. So there's going to be a couple of steps to solve this problem. First of all, we want to remember that when we look at a balanced chemical reaction, the balanced chemical reaction tells us a mole-to-mole ratio. So basically up here, you can make yourself a note. This says that 1 mole of baking soda is going to make 1 mole of sodium acetate. But we don't have anything that measures in moles. Everything measures in grams. So really our first step is going to be, all right, if I've got 15 grams of baking soda, really the first thing I want to do is I want to find out how many moles that is. And the reason is, again, because this balanced chemical reaction up here, this balanced chemical reaction tells me how many moles react. So the only way that I can really understand and compare these is to have moles of my material. Once I've got my moles of my material, I can use the fact that I have a 1 mole of NaHCO3 to 1 mole of sodium acetate. That's the relationship according to the balanced reaction, is that we've got 1 mole of NaHCO3, which is your baking soda, and that's going to react with 1 mole, or it's going to react and make 1 mole of sodium acetate. It's a 1-to-1 relationship here. So if I've got 15 grams, I can find out how many moles, and then it's a 1-to-1 ratio. So let's do that step first. So I'm going to take my 15 grams of baking soda I'm using, and I'm going to multiply it by the molar mass in order to find out my moles. This is last unit right here. This is just going from grams of our material and figuring out how many moles there are. So this is my molar mass relationship. There are 84.011 grams in 1 mole of NaHCO3. And I got that because we already calculated that up here in my molar mass of baking soda. So again, my first thing is, because my balanced reaction only tells me how many moles react and how many moles get made, I need to take my 15 grams and I need to get that into moles so that I know how many moles of baking soda I used in my chemical reaction. So according to my calculation, I use 0.1786 moles of baking soda here. So now that I know how many moles, remember the balanced reaction told me that 1 mole of baking soda is going to make 1 mole of sodium acetate. So that's actually kind of nice because this is a 1-to-1 ratio. So that just means that if I am going to be using 0.1786 moles of baking soda. Well, since it's a 1-to-1 ratio, I should make 0.1786 moles of sodium acetate, since it's just a 1-to-1 ratio. Well, the thing is I need to know how many grams, okay? Because remember, our balance doesn't tell us moles. So this brings us back to our first unit again. So again, 1 mole is equal to the molar mass. So I'm going to go up here, I'm going to look. I calculated the molar mass as 98.04 grams. So 98.04 grams in 1 mole. So this right here, going from moles of our sodium acetate to how many grams it's going to make, that's just bringing in our last unit. So I can go from my grams of baking soda. I can figure out how many moles of baking soda I used. I used the balanced chemical reaction to figure out how many moles of sodium acetate I should make. And so then I used the molar mass to figure out how many grams that would be. So if I start with 15.5 grams of baking soda, I should make, my theoretical yield should be 17.5 grams of sodium acetate. That's my theoretical yield. Now, for how many grams did I actually make? Well, here's my flask after the reaction. So I had 221.1, and then I need to subtract my empty flask. So how many grams did I actually make? I'm going to simply subtract the mass of my empty flask, and I actually got 3.6 grams of sodium acetate. So definitely not as good as my last chemical reaction, but let's go ahead and let's calculate that percentage yield that we got. So remember that a percentage yield, the way that we calculate that is we're going to take the actual amount that we got in the laboratory. So here it is, the actual amount that we got in the laboratory, and we're going to divide it by our calculated theoretical amount that we should have gotten. And then we multiply it by 100 because we do want it in a percentage. So when we go through that calculation, our percentage yield should be 3.6 divided by 17.5 times 100. So I get a percentage yield of 20.57%. Definitely not as good as the previous experiment, but here's the thing. We can see how much should we have gotten, how much did we make, and this is really important in industries because industries don't want only a 20% yield. So they have to figure out, well, what went wrong? I should have gotten 17.5 grams, but I only got 3.6. They're not going to make a lot of profit off of something like this. So that's why these kinds of calculations are important.